Hello, in this video I'm going to explain the FastSLAM algorithm to you. As this video was created as part of the seminar Planetary Exploration, I will assume that you already know how SLAM and furthermore the EKF SLAM works. In case you don't know how that works yet, there will be a video about the topic available too. Afterwards, I will dive into the FastSLAM algorithm itself. I will describe the components and explain the steps of the algorithm. Lastly, I'm going to take a look at a use case of the FastSLAM algorithm, the Kapvik micro rover. So let's start with the particle filter. A particle filter is basically a recursive base filter that has the speciality as it can deal with arbitrary distribution. So it doesn't have to assume that the world is based on Gaussian distributions. As the name suggests, a particle filter consists of a set of particles, and each particle itself consists of a unique state hypothesis, so basically an assumption of how the world currently looks, and an importance weight that is a measurement of how good that hypothesis actually is. To make the particle filter a bit more intuitive, we're going to take a look at the example of the Monte Carlo localization, which is a localization method that utilizes a particle filter, which means that a particle basically just represents a possible robot position. A particle filter as used in the Monte Carlo localization consists of three steps: the prediction, correction, and the resampling. In the prediction, we draw points from a given proposal. In the Monte Carlo localization, this would mean that we have a motion model that assumes the position of our robot after a given input and also adds some noise. This motion model is then used to create a new particle for every old particle we had before. This way our whole cloud of points moves roughly into the same direction, but some points will move, for example, 1 meter, the others, a bit shorter, a bit more to the right, a bit more to the left, dependent on how we model our noise. The next step is the correction. This is the step where we actually look at our measurements. By doing this, we can weigh every point we have by a ratio between our target, so what we measured, and our proposal, what we had before. This is based on our observation model and gives us the opportunity to rank every point by how good its proposal actually is. Lastly, we come to the resampling step. Here we now draw a fixed amount of n particles out of a given set. This enables us on the one hand to limit the number of particles we actually work with, so during the course of the filter we could actually slowly decrease them. But most importantly, this will filter out most of the bad particles. I say only most of them because it will definitely not filter out all of them, as the resampling works by picking a particle randomly, but the bigger the importance weight of a particle is, the higher the chance is to pick a certain particle. You could imagine this like this picture here on the right side, that you have something similar to a roulette wheel, where every particle gets a fixed amount of space on the roulette wheel, and the space is bigger, the higher the importance weight is, and then we just spin the wheel, put a ball on there, and see where it lands, and that's the particle we pick. This way we mostly pick good particles. Some really good particles will probably also be picked multiple times, but this will also mean that we always or usually always pick some bad particles too. This way we can keep a broader distribution of hypotheses of our world, but we'll still focus mostly on the ones that we think that are good. These steps will then be repeated over and over with the next particle set, so we go back to our prediction and move our set, then we weigh them again, and we're going to resample them over and over again. As an example for the Monte Carlo localization, we can now take a look at an animation of how this roughly works. In the scene you can see the top view of a building with its different rooms and a corridor in the middle. We initialize the Monte Carlo localization and our particle filter with basically randomly putting a particle everywhere. Because at the beginning we have no idea where we are before we get our first measurements, so we just put random particles everywhere. Then visualized in the blue lines are our laser measurements we actually get from the robot. So you can see some are shorter, some are longer. So now we weight our particles to see, okay, how good do these measurements actually fit our particles, and then we get to the resampling step. So after a first iteration, the scene will look like this. The particles already look a lot less random now, As you can see, there are barely any particles that are really close to walls because, well, all of our laser measurements were about half a meter or meter or so we can't really have our position close to a wall. But still, they are spread in all different rooms, but we can already see that our position moved, so now we're in the corridor. The position of the robot that we can see in this animation is always just, okay, what is the particle with the highest weight? That is the position we assume we currently are right now. So to say, our best guess. In a third iteration, you can now see that the particles are starting to accumulate at certain positions, and also our position jumped again, this time into the center of the corridor, so we're slowly getting a better guess. So now in the next steps, our guesses will get better and better, and we see that the particles will slowly converge at like 2 or 3 positions. So we're now pretty sure that we are probably somewhere in the main corridor. Now if we speed this up a little bit, we can see we basically have one really good guess on the left side of the corridor, but there's still some uncertainty remaining on the right side, so it could theoretically still be there. This is especially because this building is relatively symmetrical with how the doors are arranged. But now as soon as we go into one of the rooms, we can definitely rule out the bottom position, and now we are pretty sure that we are in the top room. Now that we've covered the particle filter and how it's used in a Monte Carlo localization, we can use this knowledge to now go to the FastSLAM algorithm. FastSLAM also utilizes a particle filter, but because we want to get the position of our robot and also a map, we need to change it a little bit. And because of that, each particle in the particle filter consists of a pose and the position of all of our landmarks. This basically means that for every particle we will compute an individual map. But now that our particles are a lot more complex because every particle has its own map, it's a bit more difficult to weigh each particle and make an estimate of how good they are. Because of that, we use something called Rao-Blackwellization. This is, to keep it short, basically we factorize the SLAM posterior into multiple parts. And this only works because if you take a look at the basenet on the right, given the position of the robot, so xt minus 1, xt, and so forth, if those are given, then the landmarks, so m1, m2, m3, are conditionally independent from each other. And because the landmarks are conditionally independent from each other, we can do some pretty useful stuff. So basically what we want to know is the probability of the robot being at position X with landmarks M, given the measurements Z and the inputs into the robot U. Route regularization now means that we can split those up. So the first part is, given the measurements and the inputs, how high is the probability of our position? So this is basically the Monte Carlo localization. If we just say, okay, we have inputs and position, motion model, prediction model, we can just use Monte Carlo localization for this. And the other part is given the position and the measurements, what are our landmarks. And because I said on the last slide that we already assume in this case that our position is given, all the landmarks are conditionally independent from each other. So we don't have to assume the probability for all of the landmarks together, but we can calculate it for each landmark itself. This means that if we now look at the structure of a single particle, we can see that it contains the position of a particle, so the x coordinates, the y coordinates, and our heading, and then for each landmark a single 2x2 EKF. So instead of, if we compare it to the FastSLAM, having one really big Kalman filter where all of the landmarks are in, we have a lot of extremely small Kalman filters. This has the benefit that we can calculate the small EKFs a lot faster, because the 2x2 EKF can be solved in a linear time, whereas like those really big EKF matrices need a lot of time. This way, even though we have like a lot of particles and a lot of very small EKFs, the FastSLAM can still be, well, fast. So let's take these 3 particles as an example. First step is the motion update. So we take all of our positions of the robots and move them along according to our motion model. So as you can see, most of the particles get moved roughly in the same direction, like they all get moved relatively straight ahead, maybe a bit more to the right. I mean, we also put in some noise, so they get all moved a little bit differently. And you can also see already here, you can see the landmarks. So in this example, every particle currently has 2 landmarks. And the ellipsoid around the landmarks presents the uncertainty by the EKF. The next step is the sensor update. This means now we actually get our measurements and we check where we now perceive landmarks to be. So you can see the 2 green dots are where, if the robot would be at this position, and we get our measurements where the landmarks should be, or currently are rather. And we can now use that information to weigh our different particles. As you can see, particle 1 looks pretty good. Both landmarks are perceived within the bounds of our EKF. Particle 2, not that good, maybe just a bit of a rotational error. But particle 3, yeah, something's just really off there, so that's a pretty low weight. And of course, we need to update our belief for all particles. So we take the measurement we just got, the perceived position of the landmarks, into our EKF, and just do a normal EKF update step. So to summarize the steps of FastSLAM again, first we sample a new pose. For each particle according to a motion model and some added noise. Then we compute the weight for every particle by comparing the perceived position of the landmarks and the expected position of the landmarks. This means we factor in the measurement and the covariances of the EKFs. Then we update our belief of the observed landmarks, so an EKF update step. Then we resample the particles according to the weights. So, the bigger the weight, the higher is the chance that we sample that particle and then start the whole procedure again. Here I have another animation that now shows FastSLAM in action. So we can see our currently best perceived position and the EKFs it sees. So like the blue points are the landmarks and the red ellipsoids around them are the uncertainty by the EKF. So this highlights that for every landmark we keep a small EKF itself, and the more we observe it in relation to the other landmarks, the more precise our knowledge in the position of that landmark gets. Something every SLAM algorithm has to solve is the data association problem. This means we get a measurement of, for example, 2 landmarks, but as you can see in the picture on the right, it's difficult to decide, okay, did we perceive the left 2 landmarks or the right 2 landmarks? So there are always multiple possibilities. The trick with the FastSLAM is we can just decide only for each particle. Like, it's not that big of an issue if we decide wrong with one particle, a bit more to the left, because we probably have another particle that's a bit more to the right and chooses the right 2 landmarks. This way we can actually, for each particle, just factor out errors in the robot position, because for each particle we just assume it's at the correct position. So we just have to solve the per particle data association. There are basically 2 options. First is to just pick the most probable match. So, what is the closest one, what fits best with the EKF. The other is that we pick the association, again, randomly, considering some weights. Okay, the one that is closer probably should have a higher chance of getting picked. And, putting in randomness usually always works out quite well. And generally, if the probability that we are in one certain landmark is too low, then we just say, okay, we probably have a new landmark and generate a new one. By doing this per particle data association, it's actually possible to keep up multiple beliefs in a particle cloud. If you remember in the example for the Monte Carlo localization, for a pretty long period we could hold up our belief that we could theoretically be in 2 completely different positions. So this is like one of the benefits of the FastSLAM, that we can have multiple beliefs. FastSLAM is already a relatively old slamming algorithm, which means by now there are some improvements. FastSLAM 2.0. The most important improvement is that when we are at our prediction step, so when we sample particles from our motion model, we already take our sensor measurements in consideration when doing that, so that our motion prediction is a lot more accurate. This leads to a tighter and a more accurate particle distribution. So our cloud, doesn't spread that far with every prediction step, but is, generally a lot more tighter. And by doing that, we need a lot less particles to be effective. But this is needed because, including the sensor model in the prediction step is a lot more complex. A further advancement we can do is by making the data structure we use a lot more efficient. I mean, we're working with a lot of data, like we have a lot of particles. Every particle has a lot of landmarks with a single EKF. So by organizing them in a binary tree and referencing landmarks between related particles, so if two particles that once belong together share a landmark, we can actually share those in a binary tree. Let's finish this video by looking at a use case of FastSLAM, the Kapvik micro rover. This was a Canadian project. This is a rover that never actually left Earth, but is there to test out algorithms and other control mechanisms for rover. It uses an updated version of FastSLAM 2.0. Its main way of localizing itself is done with a LiDAR, but the LiDAR scans have a really low frequency, so the rover uses FastSLAM to correct the rover position and the map between those LiDAR scans. As an input for the prediction, we get the odometry, the IMU, and the sun sensor, and can also use those for the EKF update. Combine this with a neural network that classifies the measurements and the data association of the LiDAR scan, we have a pretty robust system that can precisely get the position of our rover. Thanks for watching. I hope you now have an idea of how FastSLAM works. My sources were mainly the slides by Cyril Stashness on his lecture of FastSLAM and some information taken from the book Planetary Rovers, Robotic Exploration of the Solar System by Alex Ellery.